So in this case, I want us to understand our half-wave rectifier. Remember, as you are working with the rectification, that is simply a process where a transformer, where the transformation actually is happening of the alternating current to a direct current. So you'll be having an AC, but at the end, you'll be having a DC. So what is actually happening there? The AC voltage to a DC voltage using a rectifier, using the diodes. We have got what we refer to as the half-wave rectification. The operation is not of importance for now. In this case, we need the part of the calculations. So when you are given a half-wave rectifier, it converts an AC signal to a DC by passing either the negative or positive half cycle of the waveform and blocking the other. And that is, in that case, if you are to consider when point A, this point here, is connected, but that is the one there on the secondary side. As you can see, it's on the secondary side. So when it is positive with respect to the point B, meaning to say A is positive, during the positive half cycle of what? Of Vs. That is during the positive half cycle. What is going to happen? The diode is now forward biased because this is positive. Current can flow. And that conducts current. So you see that the output is showing that there was something there. There was something that happened, that we've got a voltage there across the diode that can happen. But what's going to happen now if you are in the negative, meaning to say B is now negative? Can there be a conduction there? No. It means the diode is now reverse biased. And this does not conduct, meaning to say there's no conduction. We move on another, so it's going to be alternating like that, alternating. So this part is not the major part that I want us to actually have. Major part is what is actually going to happen with this half-wave rectifier that we are given there in terms of its calculations. All right, so we're going to have half-wave rectifiers calculations. So the calculations are very, very important. You need to note each. If you move on to a full wave, you're going to talk of a center tap. We're going to talk of a bridge. The calculations there, they're important. So one, these calculations that we are going to talk about, they are taken at the output. Take note, they are taken at the output. So meaning to say we are referring at the output here, where we have got a resistance, there, the output side. That is where we are relating there, at the output. So at the output, one, across the resistor, we have what we call as the current for both cycles, which is the maximum current that we can have. On the secondary side, we're going to have, let us just talk of the maximum current. I'm just going to write in short, maximum current, which is Imax in that case. So definitely we'll need the maximum voltage over resistance. Remember, current, voltage over resistance. So it's Vmax over the resistance, which is, we're taking of the secondary side. We talk of the RMS values. Remember your RMS values? I talked about this when we were relating from a transformer, normal transformer, or about the RMS values. RMS value, the current RMS can be an RMS value, which is equal to 0.707 of the maximum value, or you can just write this as IM for maximum value. Same thing with the voltage. So there, guys, it's the same thing with the voltage that is going to be affected to the maximum value. Meaning to say, somehow they might give us the maximum values, and we must relate from the maximum values. They might give us RMS values. They want you to call whatever that you're given. the formula can be transposed related to what you want. So if you make this the subject, that is the maximum, you just have to divide by 0.07 both sides. So you end up with 1,414 times the RMS. So this is current to the RMS value. I talked about this also on transformers. Remember, same thing about the maximum value. Vmax is going to be 1,414 of what? Its RMS value. There it was RMS to the maximum. So on your formula sheet, you have got this formula. So you're already having, so you can take advantage of this that you're already having on your formula sheet. You make whatever that you want there the subject. But this is the relationship that you're going to have between the RMS values and the maximum values in that case. Also, we talk of the average value. So we're going to talk of the average values. So it can be the average or it can be the DC values. So let's talk of the DC current, which is also referred to as the average value. So the DC current, in this case given as IDC, is given from the maximum current over pi, which is actually, if you divide 1 divided by pi, it's going to give us something like 0.318 times what? The maximum value. So this, remember, you're talking of what? You're talking of what here? Half wave rectification. So it's only, we are on the half wave. For a full wave, it's going to be something else. So that is what you're going to have in this case. So also, if I am given the average DC voltage, I can also calculate this same IDC given the average DC voltage given the VDC. I can simply use this, but it's voltage over what? Over resistance this time. At the output taken at, remember, we are at the output. Also, another important thing, still on the average values, it'll be, let us just say A here and just say B. We're going to also talk of the average value, which is the average of the current of the voltage this time. So you're going to have average of the DC voltage, which is this one, the VDC. Since we talked about this, you also need how to calculate it. So the average value of the DC voltage can be given as VDC, which is equal to the maximum voltage over pi. So this is simply from the same calculations of the average values. They are taken at the same value, 0.318 of the maximum voltage, just like RMS values, as you can see, same value, even for the average value, 0.318 for a half wave, and it's taken from the maximum value. All this can be calculated from the RMS value. We can take it from the RMS value. So VDC is equal to approximately 0.45 of the RMS value. It's another calculation that you can work with. From what? The RMS value, given RMS value. If you're having the RMS value, you can simply use this. IDC, we can calculate it when given VDC, we can use that, and give the resistance, we can use that formula if it works. Which formula is it that you're going to apply? That is the most important part. Then also you are going to need the peak inverse voltage. So there we're going to talk of the peak inverse voltage. Peak inverse voltage. This is given as PIV, peak inverse voltage. So the peak inverse voltage, guys, is simply equivalent for a half wave. It is equivalent to the maximum voltage, your Vmax. The Vmax that you calculated. So it is simply 1,414 of VRMS. That's your maximum value. So you just need to calculate the maximum value in that case. You just need what? The maximum value. Then also you talk of the efficiency, which is another part, gain, which is important. But this one, I'm going to refer to this, actually, some calculations, so that we'll see where these calculations were taken from. That is important, but at the end, it's going to be 4 over pi squared, which is actually approximate to 40%. If you're talking about this, it's going to approximate to 40% at the end. So like I said, it's we need to talk of the calculations there, which you need to apply in terms of your efficiency. So we're gonna also try by all means just to refer to that part. But as we do understand that efficiency, guys, it's always relating DC output to the AC output. You'll be letting, in this case, DC output over AC output. That's where you end up with this, and it's for a half wave, which approximate to 80%. We're going to talk about that, this one on a special class on its own. Then another part that you also need as the part of the ripple voltage, which will give us the ripple factor. So let's talk of the ripple voltage. So the ripple voltage is given as V R RMS. That is our ripple voltage in that case. So the ripple voltage can be calculated from, again, V RMS like this is equal to 0.385 of the maximum value that is referring to a half wave. We are going to have, we're going to need this formula, and from the ripple voltage, you will need to calculate what's referred to as the ripple factor in that case. So the ripple factor is given by the letter R, or they can use the letter gamma. Remember, from our Greek letters, we have got this gamma, or they can use R in that case, representing the ripple factor. So R is equal to the ratio of the ripple voltage, which is V RMS, or ripple voltage, to the average voltage, which is the VDC average. That is our average DC. Remember, we have got this average DC voltage here. So that is going to be used, the ratio there. So that ratio is going to give us the ripple factor. In our calculations, you'll see that this will approximately to something like 1,211, something like that, which can be given also as a percentage, 121%. For a half wave, you see that it will approximate to 121%. You see that as we are doing some calculations. Then also, they'll also need you to calculate the output frequency. Output frequency. So the output frequency is simply equivalent or equal to the frequency that we originally had before. The frequency that you are given before, that is going to be still your output frequency when dealing with a half wave rectifier. So with those calculations, I think we can attempt as much questions as we can, also understanding those basics of a transformer, this and that, because as we can see, all these, they are part and parcel of our transformer. The transformer is also involved. As long you have this, you have to consider that you need the transformer calculations. So they were given an example to work with, example 4.4. Determining voltage and current in a single phase half wave rectifier circuit. The question was, determine the voltage VDC across the resistor of 150 volts here, and the current IDC at the output there flowing through the resistor. So like I said, these are output values that you're given there. So you work with what? Output values, given that it's a single phase half wave rectifier that you're given. That is the information that we just have in this case. All right, let's see. Let's see what we are given. Already our diagram shows us everything in this case. So I'm just going to answer the question here. Just going to answer our question straightforward. So VDC, how do we calculate VDC? So the first thing, you do not just answer like, what is it that you're working with a half wave? So those are the formulas for a half wave that I gave you. I'm going to talk of a full wave as we move on. So VDC, we saw that. What are we given? One, we've got the RMS value on the secondary side, meaning to say this is the one that we need because we are on the output. Remember, we work from the output side of the transformer. That is where you work with. So we're already given the RMS value there. Remember, VDC can be written in terms of the RMS value again. So that here, VDC is equal to what? 0.45 of the RMS value, meaning to say I could have used that formula, that's 0.45 times the RMS value, because I have the RMS value is given. This is RMS. So that was going to be 0.45 times the RMS value of 220. So that was going to give us 99 volts as our VDC. But maybe I'm related or I'm used to other formulas. I'm related to, maybe I'm used to other formulas. How am I going to simplify? Which formulas are these? Okay, let's get rid here. The same VDC could have been calculated from this one, 0.318 of the maximum value, which is Vmax over pi. So if you use the Vmax over pi, at least you're going to have something that is closer to the answer there because of the rounding off of the values. Remember all this other part that we are talking about. We could have calculated the same VDC that way, but let's see now, because we are limited somewhere. We are limited. We know this was going to be Vmax over pi, which is same as 0.318 of the maximum voltage. All right. But the question is, are we having it? The maximum voltage on the secondary side, on the output, are we having the maximum voltage? No. We do not have. We are given RMS value. So meaning to say you were being forced to calculate VM at the secondary side. What is going to be our maximum voltage? From the RMS value, we have to go back, guys. From the RMS value, how do you calculate the maximum? Remember, maximum values can be calculated from RMS value 1,414 times RMS value. So meaning to say, you are going to be forced to use this 1,414 or the square root of 2 times what? The RMS value, which is the one that we are given on our diagram, on our information, 220. So Vmax was going to be something like 311.08 volts. So it's now easier for us to calculate the VDC because it's going to be from any one of these formulas. If I'm using 0.318 times the maximum value, it means it's going to be 0.318 times the maximum value of 311.08. And that was going to give us something like 98.923 volts, which is actually approximately 99 that we are seeing there. It's one and the same. If you're using a pi there, if you're using this one of a pi, it was going to be VDC is the maximum value 311.08 over pi. This was going to give us an approximate value of 99.02. As you can see, they are in the same range, 99. So you could have calculated this way. It's up to you. Which way are you going to calculate? Are you going to go through the maximum value? Because you know that formula of maximum, then you relate to the VDC that you're given. Or you're just going to use the RMS value as it is. Still, you're going to have the same thing. So that was our first part of the question. Then also they need us and the current, which is IDC. So still we're going to have the same thing for the current, but this time for the current is going to be an advantage because we've got VDC and the resistor is there. Remember IDC, we've got so many formulas, but we do not have the currents now. So this thing of calculating RMS or maximum current is going to be a lot. It's going to be a lot. Yes, we can do that because we have got the maximum voltage. Then you need to use this formula, calculating the maximum current. Then after calculating the maximum current, you use IDC, which is maximum current over pi. It can work. Or you can just use this one because VDC is there and the resistance is there. So we can simply use IDC is VDC over what? VDC over R. So that is the voltage that we calculated, 99. You use the answer that you obtained there over what? Over R. What is the resistance at the output? That is of 150. So meaning to say that was going to be 0.660 amps. That's our IDC there. Or like I said, you could have used that of the maximum. Because you guys, okay, it's the way. Let's see it. Or let's say we could have worked from the maximum because we understand that IDC can be taken from this formula where there's a maximum value there. There's a maximum value there. So IDC, we saw that it can be taken from maximum value, which is the maximum current of a pi, which was the same as 0.318 of the maximum value of the current. But we do not have the maximum current. We are limited with what? The maximum current. So where are we going to obtain our maximum current? Do we have a formula for this? Yes. Once there's a maximum voltage here and a resistance, we can calculate the maximum current. So it must be maximum voltage over the resistance, of which now this one was going to limit you because you do not have the maximum voltage. You have the RMS. But remember, I calculated this when I used that formula. We ended up working with the maximum voltage where we got 311.08. If you still remember that, we had this part that I removed there. So if you're not having, then you must calculate. So you see now, guys, it's up to you. It's up to you. That's what you understand. So your maximum voltage, we calculated this. We got 311.08 over the resistance at the output. There, the resistance is 150. So it was going to be 150. You divide, it was going to be 2.074 amps, which is the maximum current that is affecting our circuit. So with this maximum current, IDC can be calculated because IDC, which is I max over pi, so you can divide this by pi, or you can simply use 0.318 times the maximum value that we got, which is 2.074. This was going to give us something like 0.659 amps. So as you can see, it's one and the same thing with what we have obtained there, 0.660 amps. It's only that there we are using rounded off figures. We are rounding off this and that. So you won't obtain exactly that. But this is exactly the same. This is the same. So you must be careful on your calculations there. Which part are you going to apply? It's in your hands. Which part are you going to use? It is in your hands. So there we can relate back to the normal half-wave rectifier that we are having. All right, another part of our question that I need us to consider, it is still on the half-wave there. There's another part there that I'm also having. And I want us to see with these formulas that we're having. Remember your formulas. Make sure that you understand all your formulas, each and every part that you are given. Understand your formulas. That is the major part. All right. Like I said, guys, there's another part here that I need. Let's hope I did not remove that. All right. So what we are going to do is to apply these formulas in our other questions. But for now, let's just revise them. Revise everything. All this. Just have a revision. Then we shall refer to other questions where other questions that we need from a half-wave rectifier can be applied. But for the formulas, this is what you might need. If there's a formula that you might need in this case, let me know so that we can see if there's a formula that can be added in our revisions also.